afternoon again. So today we're going to continue on application of first law of thermodynamics for open systems. So far we covered nozzles, diffusers, turbines. Today we're going to we also covered compressors and pumps. Right? Today we're going to cover throttles and heat exchangers. Okay? Throttles are also known exchange valves, and they are widely used in refrigerators. And heat exchangers, we will just look at the heat exchangers from a thermodynamics point of view. Heat exchangers, if you want to get deep into it, it's a completely different class. Okay. It is categorized under heat transfer, and you can get a big project from a heat exchanger. Design-wise, heat transfer-wise, thermodynamics point of view. We are not going to get into that deep, but we will look at how first law of thermodynamics can be applied on those devices. Okay? Okay, let's start. So we'll continue on applications. Of the first law for open systems. And so far we covered nozzles and diffusers, and turbines, compressors, pumps, and today we're going to start with throttles. Okay. Let's remember a couple of things that we covered so far, and they will be used for throttles and other devices. They're also considered open system devices. Okay? So first one was a steady state equation, right, for open systems. It was Q dot, right? Summation of all the inlets, H in, kinetic energy in plus potential energy in, equals workshop plus summation of all the outlets times H valve plus kinetic energy out plus potential energy out. Okay. This is for steady state. Steady state, or
it's kind of off the right side.
And we further simplify this equation for one inlet, one outlet at steady state. Now it's Q minus workshop equals healthy difference plus kinetic energy difference plus potential energy difference. Throttles. Throttles are usually one inlet, one outlet devices. Okay? It has a valve in the middle, and it is adjusting the pressure difference in the cycle. And we will see how it is used in a refrigeration cycle usually, as I said, towards the end of the semester when we come into cycles, power cycles, refrigeration cycles, heat pump cycles. So it has one inlet, one outlet. We call inlet 1, outlet 2. Okay? That's why our simplified equation for one inlet, one outlet for steady state equation, Q minus work done is delta H plus kinetic energy plus potential energy from 1, 2. Okay? For throttles, usually, as you can see, it's very simple stuff. Well, again, from a thermodynamics point of view, actually it is not. So, ideally, Q is 0. Okay? There's no shaft in the throttles, and kinetic energy and potential energy difference are negligible, almost 0. So what we have left is, therefore, delta H is 0. Okay? Example. Steam flows through a throttling device under the following conditions. Steam enters the device at 30 bar and 240 Celsius and exhaust at 7 bar. Okay. And B enters as saturated vapor at 8 bar and exits at 3 bar. Determine the downstream temperature for each one. So this is all about reading table. Okay. So we'll use one inlet, one outlet, steady state, first law of thermodynamics for open system equation. We simplify it, we already did it. It gives us delta H equals 0, which means like delta is enthalpy, the inlet and exit are equal, right? So by knowing that, if I know one condition extra, temperature or pressure, in this case, I know the pressure. I retrieve this from the table, okay, and determine my temperature and other properties. Okay? A is for the throttle. One inlet, one outlet. For the case case, for the first case, peak pressure is 30 bar, temperature is 240 Celsius, right? Enthalpy will be 2,824.3 kilojoules per kilogram inlet. Okay. Make sure you can read those values from the table. Go and double check. It's not going to take more than a minute. Inlet and outlet. And I know my outlet pressure is 7 bar. Q minus work shaft equals delta H plus delta kinetic energy plus delta potential energy. For an ideal throttle, Q work shaft kinetic energy and potential energy is at 0. And from here, kind of H2 equals H1, which is 2,824.3 kilojoules per kilogram. If you go and check the table, A3, if I remember correctly, this value is in superheated region. If you go and check in the superheated region on the 7 bar, this value should lie between 180 and 190, or 200 and 180. Okay? So you need to interpolate. By doing linear interpolation, temperature at the exit T2 will be 1 degree Celsius, 200 minus 180 Celsius, times 2,824.3 kilojoules per kilogram minus 2,799.1 kilojoules per kilogram divided by 2,844.8 kilojoules per kilogram minus 2,799.1 kilojoules per kilogram. From here, T2 should be 191 Celsius. Okay. Part B. We again have throttle, but the conditions are different. Boundary conditions. One inlet, one outlet, 1 and 2. Right? Inlet condition pressure is 8 bar, and substance enters as saturated vapor. Exits at pressure to V bar, and we are asked to calculate temperature. Okay. Enthalpy can be found from the table at saturated vapor. Enthalpy H1 will be 2,769.1 kilojoules per kilogram. Right? Again, using first law of thermodynamics. So delta H of kinetic energy plus potential energy. Okay. After eliminating negligible terms, Q, W, kinetic energy, and potential energy, H2 will be H1 equals 2,769.1 kilojoules per kilogram. Again, this should be superheated. Temperature exit by using interpolation 133.5 Celsius plus 160 minus 133.5 Celsius, 2,769.1 minus 2,725.3 kilojoules per kilogram divided by 2,782.3 kilojoules per kilogram minus 2,725.3 kilojoules per kilogram. I'm not sure if you can read this. Okay. Temperature from here, T2, 153.9 degrees Celsius. It's very straightforward. I think you have one question about this in your assignment. So I think it's enough for Throttle. Okay. So let's move on to the next device. Which is heat exchanger. Okay. Any questions on this? Yes.
How do we assume that it's been superheated?
How do I assume? I didn't assume, I checked on the table. So I know my enthalpy at the inlet because I know the condition at the inlet.
Yeah.
Right? So from, first of all, thermodynamics for one inlet, one outlet, a steady state condition, right? I found my exit enthalpy as well. Right? By knowing this, you know your exit pressure. If you check your enthalpy, they should be in superheated. That's how I know. And knowing your enthalpy, you can find where your temperature lies, which values, okay, on that superheated table. Clear? Another question? Okay. All right. So we covered nozzles and diffusers, turbines, compressors, and pumps. And we also covered throttles. Okay. Now, heat exchangers. We have two types of heat exchangers. Okay? One is closed system heat exchanger, or another one open. Otherwise, they call it separating wall or closed heat exchanger, meaning that you have one cooling substance and you have one hotter substance. They transfer heat between. And they determine the type of heat exchanger depends on if they mix or if they don't. Okay? If they don't mix, they say that there's a wall between and they don't mix. They only transfer heat and energy between them. And there are other times they're mixable and they mix and come out as a mixture. Okay. First one we will look at is closed one, separating wall, or closed feed water heat exchangers. Okay. Heat exchangers one inlet. Again, I try to simplify as much as I can by using one inlet and one outlet. And I try to emphasize that's not always the case. Okay? You might have multiple inlets and multiple outlets. Same device, multiple inlet, multiple outlets. Then we have one inlet, one outlet. One, two. 1, 2. 3, 4. Heat transfer takes place between. And the one on the bottom is cold fluid. In this case, could be on the top, doesn't matter where it is. And on the top is hot fluid. So far, in this open system devices, it was pretty straightforward to determine my control volume. It might be tricky for heat exchangers. What is my control volume here? Anyone? Yes, Thomas.
The entire box, the top and the bottom?
You mean both of them?
Yeah.
That's one case. Remember, my boundaries. When I determine my boundaries, I determine to allow transient energies or mass passing through my boundaries. If they pass, I can calculate, I can keep track on it. Because I know what enters and leaves. If I put my boundaries on top of something, and if that property or feature of that problem stays in that control volume, I have no control on that. Because it never leaves my boundaries. Okay? Clear? So in this case, if you choose your boundaries covering this whole system, okay, you can calculate Q. It's either given or somehow you should know because it doesn't leave your boundaries. Clear? Sometimes you have to calculate or you need to calculate Q. In that case, you determine your boundaries based on that. Sometimes you need to find 3 inlet of cold side or outlet of hot side, etc. Okay? Right. Anything else? And also, this inlet and outlet, from a heat transfer point of view, this inlet and outlet, if I switch them, it affects my heat transfer efficiency. Just let me know, okay? That's a design point of view. Let's look at one example. Any questions?
So, for this one again, we know what he is technically, or is there
Not always, sometimes. Sometimes you are given, sometimes you need to calculate.
Okay, but in this case,
We don't know.
we don't.
Okay? What I'm saying is you determine your boundaries based on the problem. Okay? Dry air enters an air conditioning system at 30 Celsius and 0.11 megapascal at a volume flow rate of 1.2 meter cube per second. The air is cooled by exchanging heat with
Yeah, just shift the page.
a stream of refrigerant 22, which enters the heat exchanger at -10 Celsius. And a quality factor of 20%. The refrigerant leaves as a saturated vapor assume constant pressure for both streams. 22 kilojoules per second of heat is removed from the air determine A, the flow rate of refrigerant 22 in kilogram per second, and B, the exit temperature of the air in degrees Celsius. Okay. We have a heat exchanger with one inlet, one outlet. One inlet, one outlet. Q is given 22 degrees per second. T1 equals 30 Celsius. And volumetric flow rate is 1.2 meters cubed per second. And air exits pressure 11 megapascal. And not the temperature. So here is outside as hot fluid, bottom cold fluid. So for refrigerant, -2, temperature is -10 Celsius, and the qual factor 20%. We are asked to find mass flow rate and leaves at 110 Celsius at saturated vapor. Okay, in this case, where is my boundary condition? Where's my boundary?
Both sides.
Both sides. Okay. You don't have enough information to use both sides because you have two unknowns on both sides. Okay? I'll show you. The equations, right? Okay. Volumetric flow rate is mass flow rate times volume. Set of equation because one of our substances is ideal gas, right? I also know Q minus workshop equals delta H. That's going to be plus what times 1H. Well, first I'll come down. So in the first case, case A, I'm asked to calculate flow rate of refrigerant 22. Okay, so in that case, I will choose my boundary condition around the cold fluid only. So if I choose okay, let's show it this way. So this is 3, 4, okay. Temperature -10 Celsius, qual factor 20, leaves at -10 Celsius. Okay. What is my enthalpy at the inlet? This is cold fluid. Only refrigerant 22 cycle. I put my boundaries Okay? So I know my inlets, outlets, Q enters my system. Also, I have an inlet from boundary 3, and I have an exit at point 4. But 2 inlets, 1 outlet. And Q, I don't have work. That's it. Now I can find my enthalpy at the inlet. Now,
Equality formula. Equality formula. And
right, I have a quality factor. What does it mean?
So you need to saturate the equilibrium.
Right. Means it's under the saturation curve. Right? So I have a mixture. Now by using that information, and I also know how to find my enthalpy and my quality factor. Correct? I know my HF, I know my HF and HG, and as a difference, I know my quality factor X. Right? So I can calculate my HG. HF is 33.54 kilojoules per kilogram plus 0.2. HG is 246.15 kilojoules per kilogram minus HF is 33.54 kilojoules per kilogram. Sorry for shifting in dozen. So 246.15 minus 33.54. And from QH3 will be 76.46 kilojoules per kilogram. I know my enthalpy inlet now. Now I can write my first law of equation for inlet and outlet because I know most of everything except the condition is stated. Okay? Q minus workshop equals mass flow rate for refrigerant 22. Enthalpy difference from 3 to 4, kinetic energy difference, 3 to 4, and potential energy difference, 3 to 4. For a heat exchanger, most of the time workshop is 0. There's no shop in heat exchanger. Kinetic energy, sometimes negligible, not all the time. Potential energy is usually negligible, right? So these are the terms for this question, particular question we can neglect. I know my Q, right? I know my enthalpy difference. I should know. I should be able to calculate. Okay. And flow rate from Q will be Q over delta H, right? Which is H4 minus H3. Right. I know my exit condition too, and temperature, saturated vapor. It's given in the problem. I forgot to put it here. So that means I know my enthalpy at the exit as well. Okay? So for 22 kilojoules per kilogram, in this case, Q is what? Plus or minus? In this case, it's plus. But if I look at it on the hot side, it will be minus. Okay? So be careful what you are doing. So So H4 is 246.15 kilojoules per kilogram, and H3 is just calculated 76.46 kilojoules per kilogram. Okay? And from here, mass flow rate for cold side should be 0.13 kilogram per second to provide or extract this much heat from the cold side to satisfy the condition. Clear? B. Now we will choose the control volume on hot side because we are asked to calculate the exit temperature of the air, right? Air is the one being cooled down, given the heat outside, right? So I will put the boundary around the air. So choose a control volume air only. Okay? P1 over P1, right? My R is for air is 0.287 kilojoules per kilogram Kelvin. Okay? Temperature is 30 Celsius or 303 Kelvin. Pressure is 0.11 megapascal or 110 kilopascal. Specific volume will be 0.79 meter cubed per kilogram. What is mass flow rate? Volumetric flow rate over specific volume. Right? I know my volumetric flow rate 1.2 meter cubed per second. Right? Specific volume is 0.79 meters cubed per kilogram. This will give me 1.52 kilogram per second. Right? Q minus work shaft equals mass flow rate of hot fluid, enthalpy difference, kinetic energy difference between exit and inlet, the hot stream. Okay? Our work, kinetic energies and potential energies are negligible. I know my Q, right? It's given in the problem. I just found my mass flow rate. How do I find my H? Anyone?
You find H1 from the table.
Okay, what is it? How would you count it?
Using specific volume and temperature.
Specific volume times temperature. There is no such a thing.
Well, I meant interpolate.
So what is it? Just tell me. How would you find enthalpy here?
And,
Anyone? You should always read problem statement carefully. Carefully. What does it say? The problem statement, it says, assume constant pressure for both streams. What does it mean?
Would that mean that the fluid is the same?
Okay. It means you can use constant specific heat model, right? So what is delta H from a constant specific heat model? CPdT. All right, thank you. Mass flow rate, sorry, Q, right? With the mass flow rate, hot stream, Cp times delta T. That's it. Right? Q, mass flow rate, Cp, delta T. I can now find T2 from T1 plus from 1 to 2, heat transfer from 1 to 2, and flow rate at a hot stream and Cp. Okay, I will leave this to you to find, read from your table, but make sure you can do it. Right? Temperature inlet of hot stream is given as 30 Celsius plus minus 22 kilojoules per second. Why is it minus? Because it's leaving, right? Careful with the sign conversions. Always. Okay? Minus 22 kilojoules per second. And mass flow rate is 1.52 kilogram per second. And Cp 1.005 kilojoules kilogram to the Kelvin. Okay. And T2 from here will be 15.6 degrees Celsius. Okay, let's do one more example. Any questions on this? We have a couple of minutes for those who couldn't catch. So one more example. Liquid water at 5 bar and 140 Celsius flows through inside 20 tubes of shell and two heat exchanger. Heat exchange. At a total rate of 240 kilograms per minute. And it leaves at 4.8 bar and 60 Celsius. Water is cooled by passing air initially at 110 kilopascal and 25 degrees Celsius. Sorry, I sometimes forget. About that's on inlet volume. Volume rate of 1,000 meters cubed per minute. Through the shell of the heat exchanger. The exit pressure of the air is 105 kilopascal, and we are asked to determine A exit air temperature in degrees Celsius, B inlet area for airflow in meters square if velocity is 25 meters per second. C inlet water velocity in meters per second if each tube has a diameter of 2 centimeters. Alright. So we have a heat exchanger, same system, one inlet, one outlet on each side. But this time we have a tube inside. That's the design of heat exchanger. That's how it works. Okay, you have small tubes, usually made out of copper, and your fluid runs inside those tubes. Why? To increase the surface area, and you run through it. The pressure changes, etc. So this is just a simple thermodynamics point of view. And we know the number of tubes, area, one side, one inlet, and outlet, etc. Okay. The one inlet, one outlet, closed shell heat exchanger. I can get done with this. one inlet, one outlet, one inlet, one outlet. 1, 2, 3, 4. Hot fluid. Cold fluid. I know air, in this case, air is coolant, right? In the previous example, the refrigerant was coolant. Cooling the air, now it's air cooling the water. Volumetric flow rate is given as 1,000 meters cubed per minute. Pressure 1.1 bar. Right, temperature 25 degrees Celsius. Velocity 25 meters per second. Pressure exit of a hot fluid 4.8 bar. Temperature 60 degrees Celsius. Pressure 1.05 bar. And pressure 5 bar. Temperature 140 degrees Celsius. Diameter 2 centimeters. And number of cubes 20. This cube, I don't know. Okay. Let's start finding Q. What's my Q? Q water minus workshop, mass flow rate water, delta H, right? Is water from 1 to 2. Kinetic energy difference, 1, 2, and potential energy difference. Kinetic energy and potential energies are negligible. Q water will be equal to mass flow rate of the water times enthalpy difference. Now, hot 3, exit 1, inlet 1, exit 2. Or mass flow rate of the water, H minus H1. Okay. Both sides are compressed liquid. On the hot fluid side, I know because the conditions. Yeah. All right. I determine my phase based on the conditions I'm given. Inlet and an outlet of the hot. Okay. You determine it from the table. If you're on the left-hand side, the saturation temperature or based on pressure, right? If you're lower than the saturation temperature, you're in the compressed liquid region, right? Or if you use the temperature table, if your pressure is higher than your saturated pressure, you're in the compressed liquid region, right? That's the case in both inlet and outlet from hot steam side. So for compressed liquids, by knowing that, you can determine your H1 and H2. H1 and H2. H1 is 589.13 kilojoules per kilogram. H2 is 251.13 kilojoules per kilogram. Then Q, water. Now I can find my Q water because I know my mass flow rate is 240 kilograms per minute. 251.13 kilojoules per kilogram minus 589.13 kilojoules per kilogram. Seawater would be minus 81,120 kilojoules per minute. Now I switch my interest to other side of the heat exchanger. On cold side, I can find my specific volume, the inlet. I know my pressure, temperature. I also know my gas constant for air. Going to 7 kilojoules per kilogram Kelvin. Temperature 298 Kelvin. The pressure is 110 kilopascal. Right? The specific volume from here will be 0.778 meters cubed per kilogram. Mass flow rate inlet for cold stream equals volumetric flow rate divided by specific volume. Thousand meter cubed per minute given in the problem. My flow rate on the cold stream, right? And specific volume is 0.778 meters cubed per kilogram. And mass flow rate for air 1,290 kilogram per minute. Okay. If I write my first law equation for the cold side, right? After eliminating the workshop kinetic energy difference and potential energy difference, but I cannot neglect my kinetic energy in this case because I know the velocity. Okay. So Q air and air, right, delta H. But here, right, velocity is given for another purpose. I'll explain shortly. From 3 to 4, right? What is my Q air? Do I know my Q air?
Positive 81. It's a positive 81.1.
Right. So Q air is minus Q water. Right? What else? How do I find my enthalpy? Cp delta T. Okay. T4, I know my T3, but I don't know my T4. T3 will be plus Q air divided by and air times Cp air. T3 is given 25 Celsius. Qn is 81,120 kilojoules per minute. Right. Mass flow rate is 1,490 kilograms per minute times 51.005 kilojoules per kilogram degree Kelvin. And T4 from here will be 87.57 degrees Celsius. Area, the inlet, number mass flow rate, air times specific volume over velocity. Remember, mass flow rate, area times velocity over specific volume. Right? Mass flow rate is 1,290 kilograms per minute. Specific volume is 0.778 meters cubed per kilogram. Velocity is 25 meters per second. Okay. I need a unit conversion here, 60 to 1 minute. That should be good. Area from here at the inlet falls 3.667 meters square.
You started over. Okay.
Okay. Inlet velocity for the water if the diameter of each tube is 2 centimeters. Right? What is the velocity? How do I find my velocity? Velocity equals mass flow rate times specific volume over an area. What is area in this case? All those tubes, okay? Number of tubes and each diameter area, right? Mass flow rate and water flow rate and specific volume over n T d square. T square over 4 is an area for each tube, and I have n of those. Area is T square over 4 and I have 10 of those. And V1 is here 4 times the mass flow rate, 240 kilograms per minute. Specific volume is 1.04 times 10 to the minus 3 meters cubed per kilogram divided by n number of cubes. I have 20 cubes, P 2 centimeter meter square times 60 seconds per minute. I need a unit conversion because mass flow rate is given in units. And velocity inlet water stream, or hot stream in this case, is 0.66 meter per second. What was the velocity on an air side? It's 25 meters per second. So how slow on a water side? 0.266 meters per second, not even 1 meter per second. Why? Because water removes more heat, way more than air. I need to run it slowly, and mass flow rate will be way less than the air side. Okay. Any questions on this? Yes.
What is that little value next to the 20? Is it like a little R or?
Hi.
Oh. Thank you.
Is it better? Comes from here. Okay. Any questions? Okay, that's all for today. I'll see you on Thursday. Thank you. Let me know if you can see the assignment. Do you have an assignment due next Tuesday? Next Tuesday? Yes.
Yeah, you can see it.
What is it?